Okay, let's talk about the names for these. Let's start with this one up here. What would you call this?
4-octene.
Good, 4-octene. Good. And then what would this one be? 1-pentene. Good, or we could just call it pentene. Okay, next question. Okay, I'm going to go through a few and then there's one for you guys to practice. So I look at this molecule, I look at the longest carbon chain with our double bond, and either way I number it, 1, 2, 3, 4, or 1, 2, 3, 4. The double bond is at 2. Okay, so my parent molecule, let me turn on my pen. The parent molecule here is butene. And it's 2-butene. So this 2 corresponds with, it's telling me this 2, the butene is at 2. The double bond is at 2. Okay, and then the next thing we would want to do is to reduce the methyl. Because this is symmetrical, we could pick this way or this way. We're going to pick this way, 1, 2, so that the methyl group is at the 2 position. So this would be 2-methyl dash 2-butene. Okay, so we're using the same things. Now we just throw in some double and triple bonds.
Oh, this is the wrong class, sorry.
No, you're fine. All right. Oh, she's probably looking for her. Oh, for as well. Hey, they're outside. Yeah, they're outside. Just right here. So you'll have to go, I think, out and around. Okay. Okay, so this one, I have to recognize this as a carbon, not a chlorine, or a chlorine, not a carbon. And then I look at my longest chain with the multiple bond. And so I'm going to start from here. 1, 2, 3. That makes the chlorine at a lower position, and that also makes this methyl group at a lower position. So I will number this 1, 2, 3. So then my parent carbon will be pro with a E and E at the end, propene. And then I have a methyl at 2, and I have a chloro at 1. So chloro is going to come first alphabetically. So we've got 1 chloro, oops, 2 methyl. And then I need to say where my double bond is. This would be at the 1 position. Okay. All right, go ahead and try this one. Okay, just for time, we're going to jump in and do this one. So what would you call this one? What would be our name?
Would it be 4-methyl-pentene because some prioritize where the bond is?
Good, yes. Good, perfect. So we have pentene. We're going to number from this side to prioritize the other one. Perfect, good. All right, go ahead and try to draw these alkenes or alkynes. They're both alkenes, actually. Okay, take a few more seconds and then I'll show you what these look like. All right, here is what those look like. Okay, questions? So this would be our condensed structure. I didn't specify, so maybe you drew the line structures. That's fine. But in Alex, just make sure you're drawing either the condensed structure when it asks for that, or the line structure. Okay.
I have a question.
Yes.
So on the top one,
Yep.
wouldn't the chlorine be on the other side? Because it's 113, right?
Here.
Yeah.
So we've got one chlorine, one chlorine, one
Or
chlorine.
never mind. Maybe it doesn't matter if it's factors. I was reading it left to right. Does it not matter?
Oh, so if you had your molecule drawn this way,
Yeah.
that's the same molecule. Same molecule. It's just flipped.
Okay, that makes sense.
Yeah. So that would be like looking at my pen this way or looking at my pen this way. It's the same pen. Yeah, good question. We're gonna talk about that in a minute. All right, so not the last, there's two more things we need to talk about. One of them is that when we introduce double bonds or triple bonds to a molecule, that makes the molecule rigid. Okay, so I have some models up here. I'm gonna pass them around. So if I look at this molecule, where I have these 4 electrons being shared between 2 molecules, that represents a double bond. Okay. Down here, I have 2 electrons shared between the molecules. This is representing a single bond. And if I try to spin this single bond, it spins pretty well. Okay, it's really easy to move that. Okay. So what I want you to notice while you're playing with these is that if I have 2 carbons next to each other, and they're next to a single bond, that's really easy to rotate. And then the hydrogen-hydrogen distances on these adjacent carbons, the distances between those hydrogens can move. Okay, I can rotate around that single bond. There's an Alex topic, and it's going to give you a flat molecule. And you're going to have to kind of imagine a 3D structure of the molecule and realize that if there's a single bond, that can rotate. And you have to recognize, if I have a single bond that rotates, which bond distances can move. Okay. Notice that the hydrogens on the same carbon can't move. Okay, they're stuck. But the hydrogens, the distances between these hydrogens can move. And then if I go over here, I have this double bond between these 2 carbons. Those are fixed. So the distance between this hydrogen and this hydrogen on these adjacent carbons are locked into place because of this double bond. Okay, so this is really a tricky topic because you have to think from a flat picture and kind of picture what's going on in this 3D molecule. Okay, so I'm going to pass those around. Kind of try to get in your head which bond distances can move, okay, and which ones are locked. Okay, so double bond is really hard to move. The single bond you can rotate, and the different distances move. I want to look also really quick at the simulation. I'm also trying to get through so we have a little bit of time to work, but it is a short day. So if you can practice this, if you can think in 3D spaces, it's going to help you a lot. So here is an ethane molecule. We have a single bond. The hydrogen-hydrogen distances on the same carbon won't move, but if I rotate, then the hydrogen-hydrogen distances between adjacent carbons can move. So this hydrogen can get away from this hydrogen if I rotate it. Okay. If I look at, I think this one's a double bond, I can kind of rotate these double bonds, but it's just flexing. It's really hard. I can kind of drag and drag and drag, and it kind of moves a little bit, but this double bond is locking these two in place, okay? And the last one I want to look at is this molecule called biphenyl. So we have two phenyl rings, and they're connected by a double bond, or a single bond, excuse me, a single bond here. This carbon, single bond into this carbon. Anytime I introduce a ring, that is also introducing a rigid structure. So if I look at this hydrogen adjacent to this hydrogen, these are both in a ring. This hydrogen cannot move away from this hydrogen. They're locked. But if I spin this molecule, let's find a good angle. If I spin around, it's not moving. There you go. If I spin around this single bond, that was kind of hard to see. These hydrogens can kind of get away from each other at the edges, okay, because they're on different rings. And because that center bond is a single bond, we can rotate around single bonds. Okay, so this is kind of a tricky topic. I would try to practice this one, get it out of the way early, and then I would review it a lot. Okay, this is kind of, because they're not going to give you a 3D structure, they're not going to give you a rotate button, you're going to have to do it from a flat structure. Okay, let me know if you have questions on that as you're going through that. Okay, we did both of those, good. All right, the last topic that we need to talk about today is isomers. If we have the same formula and we have different structures, different connectivity, we call that an isomer. So these two molecules, they have different names because they're different. If we look here, this bromine is connected at the end. This bromine is connected in the middle, but both of these molecules have 3 carbons, 7 hydrogens, and 1 bromine. So when we have the same atoms connected differently, that's called an isomer. And we're going to talk about a few different types of isomers. Today we're just talking about, this is called a constitutional isomer. So you are going to have to look at a molecule and decide if it's an isomer or not. So we're going to look at what we think about when we're deciding this. So these are different molecules, they're going to have different reactivity, they're going to have different physical properties. So they are different, they just have the same chemical composition. Nice. There we go. So this is what questions I would ask to see if it is an isomer. Yep. So the first question I'm going to ask is, do they have the same chemical formula? So I think the best way to do this is just to do it the long way and write out what the chemical formula is for each molecule. And then the second question is it a different molecule? Like Mia was saying earlier, we can represent the same molecule and we can flip it upside down. So you have to recognize, is this a different molecule or is it the same molecule just rotated? Okay. So look, this is the questions I would ask. And if both of these are true, they have the same chemical formula and it's a different molecule, then it's going to be an isomer. Okay. So go ahead and check on these two pairs of molecules. Are they isomers? Okay, let's talk about this. Okay, so the first one up here, do you guys think these are isomers?
Wait.
Okay, some of us say they do, and some of us say they don't. So the first thing that I would do is I would look in, are these the same molecule? Is it the same? Okay, they're not the same molecule. That's a good thing for an isomer. Now we need to write out the formula. So what did you get for the formula for this molecule?
Do I just tell you like how many carbons?
Yeah. Yep.
5 carbons and 12 hydrogens.
Okay. All right, and how about this one? What's the formula?
Carbon, same 13 hydrogens.
Okay, we have, this happened in our class yesterday too. So we've got carbon, 3 hydrogens here. We have 2 hydrogens here because carbon to carbon, carbon to carbon. And then this carbon has 3 things already, so we just have 1 extra hydrogen. And then this is a methyl group at the end, methyl group at the end. So then if we add those up, we should get 12. So we've got 3, 3, 3, that's 9, 10, 12. So we have the same formula, and it is a different molecule. So yes, these are isomers. Okay, very good. And how about this one? Is this a different molecule? This is not a different molecule. If we rotate this, or if we fold this, if this was a paper, if we folded this on top of itself, this would be the same molecule. So it can't be an isomer if it's the same thing. Okay, so this is not an isomer. Okay, questions on that? This is kind of tricky, but once you get it, I think it'll be okay. Okay. All right, that's our last slide. We do only have 10 minutes, but use this 10 minutes if you haven't turned in your lab, maybe do that. If you have some time, if you think you can get a few Alex topics, then that would also be